difference here is that the program, the model has been generated by the computer. So that's one way of seeing machine learning. We need to remember this for the next slides because we are going to give more explanations about machine learning. One of them is to see machine learning as a subset of artificial intelligence. So artificial intelligence is described as the ability for the computer to imitate human behavior. But this definition can be a little bit vague, a little bit broad. And actually today we can say that artificial intelligence, it's mostly a marketing term. It's heavily used in marketing, and that doesn't mean much. Because if we just keep this definition of imitating human behavior, any hard-coded program in a way, even a hello world, we can say it imitates human behavior. So we need to go a bit deeper and come back to what we explained, that it imitates human behavior, but also the program itself is written by the computer. And finally here I've put deep learning as a subset of machine learning because probably you've heard about this field, deep learning. It's essentially the same thing as machine learning, except that it uses a special type of algorithms, neural networks, and they have usually many layers, they are deep, so it's called deep learning. But essentially it's the same thing as a broad concept. So now we have seen machine learning in the context of artificial intelligence, but another way of defining it is to understand the skills that are needed to do machine learning. And here we can see 3 skills. So it's not exactly like software engineering, where mostly you're interested in, hacking skills and coding. Of course, the business expertise is important as well. But here, on top of that, we also need some math knowledge, some stats knowledge. So we have these three skills: coding, math, and business expertise. And the 3 of them are really important. I would say that in a team, of course, it's easier in a team to get these 3 skills, but as a data scientist, as a machine learning engineer, it would be really important to have good foundation in programming in order, to be able to produce and move forward. I've seen doctors in statistics or mathematics without these programming skills, and it's very difficult for them to do anything very useful for the business. So don't underestimate the programming skills that you will need for this. And the good thing with Azure Machine Learning is that many of the difficult parts of the engineering, like deploying a model, like monitoring, like doing DevOps, we'll talk about it, those are really made easy with the platform. So we can rely on the platform for many things. Actually, we can even rely on the platform for no-code solutions. That can be a very good way to start with machine learning. Soon, if we want to go deeper, of course, we'll need those hacking skills. And I want to emphasize also the need to have a business expertise. The business knowledge is very important. So either you will have to, study the application field, or you will have to sit with the customers or with the users to really understand what they want. And this we can also see it when we talk about the machine learning process. This is the typical process that is followed in any machine learning project. And it starts with business understanding. So just saying that, it's already something big, because if you've ever done anything in machine learning or data science, the first thing that you get as an engineer is somebody is throwing you some data and says, okay, get me something interesting from this data. That's the wrong approach. If just doing that usually will not lead any meaningful result. The first thing we need to do is business understanding. And I can give you an example. I was working for a company. The goal was to try to identify suspicious cargo ships in the channel between France and England. So there are tools to monitor cargo ships to see their speed and their direction, their weight, etc. And the idea was to collect this data and to build some kind of anomaly detection. The problem was that we had no idea what was an anomalous ship or how it was behaving, what was suspicious or not. And we had no experts in the team, and we had no access to any experts as customers, or we just had some data. So very, very quickly, we realized that we wouldn't be able to do anything with that without the expertise, the business understanding of identifying what is. There will be the data understanding. So as a second part, we need to understand what data is available. Where is the data? Do I have access? Can I request access? It's ideal, of course, when your data is already in your data warehouse or in your lakehouse, and you can have easily access to it. Otherwise, you will have to do some data engineering work to move the data around, to make it accessible, to make it also maybe centralized so that you don't need to pass files around to the team. That's also important. And then we have the major step, the data preparation. So we say that it's about 80% of the work, preparing the data. So what does that mean? Of course, it's related to this gathering the data and putting it in the right database. But then there will be a lot of work to explore the data, do an exploratory analysis, understand what columns do we have, what do they mean, are they clean or not, how they're correlated between each other. Maybe do some data engineering and feature engineering and increase the value of the data we have. So there will be a lot of work here. And we can do some of this work on the platform in an automated way, but most of the time, of course, to have better results, we will have to spend a lot of time in that. So that's why the role of data engineer, maybe you realize, is gaining momentum, is more and more famous, because the data scientist, the one actually working on the model, does a very small amount of the job. Most of the job is cleaning and preparing this data. So don't forget that part. Of course, in the last few years, the modeling part was presented as more interesting, but we realize today that this is not what will be the biggest factor for a successful project. Modeling can be quite easy now. So of course we have this part next, modeling. I can use my pointer as well, where we'll build the model, select a model, and we'll see in the next segment how we can improve that. We'll also see in this segment how to choose our algorithm, etc. So if you're not familiar with machine learning, that would be interesting. And most likely we'll have to go back to data preparation after modeling, because there is a limit to what we can achieve with good modeling. Sometimes we'll have to go back to improving our data to get better results. And that goes hand in hand with evaluation. We want to constantly evaluate our model, see how we're doing. And finally, the last part, which is very much facilitated with Azure Machine Learning, is the deployment. Because it's quite easy to just use your laptop and do some Python or some R, and you create a model with some data. Now the big question is, how are you going to put it in production? How are you going to make it available to other teams, to other products, other applications, so that they can actually consume your work? So this is not an easy one. But with Azure Machine Learning, in one click, we can do that. And with the deployment comes also the monitoring. And we will see also what kind of monitoring we're interested in Azure Machine Learning and how we do that. So this is a broad view of the process. And just having this big idea in mind will help us also for the demo to understand what we're trying to do here. So that was machine learning, the definition. We saw different angles of explaining what is machine learning. Now we are going to talk about Azure Machine Learning for a few slides. And I would like to start with this one. What is Azure Machine Learning? We can say that Azure Machine Learning is a platform for operating machine learning workloads in the cloud. So platform is important because it means that you can build on top of a platform. It's not a service that you're going to just consume, and it's a platform where you can actually build your models, build your use cases on top of it. Now, there are many features of this platform. First of all is that you get scalable on-demand compute. Of course, it's in the cloud, so you get this from the cloud, scalable on-demand compute. And this is very good for data scientists, very useful, because sometimes the training part of a model, or just processing the data, can take a lot of time, can take hours, days sometimes. And so if you have just a laptop, what do you do to speed this up? Do you buy a new CPU and change it in your laptop? Not really. So having this, ability to just select a new machine like 10 times bigger, 100 times bigger, just with a click is very, very practical for data scientists. And it's not necessarily more expensive because, if your computer is 10 times more expensive, but it's 10 times faster, then maybe, you pay the same price. But you gain from the feedback loop because you have answers and you see if your new model is actually better or not much faster. So that's a huge gain when we work. We don't need to wait 2 or 3 days to know if what we've done is good or not. So here, don't underestimate the value of having a scalable compute. It's very powerful, very useful. Also, comes with the platform data storage and connectivity. And this also is very useful to have a robust and enterprise solution. If you don't have that, think about it. How do you operate if you don't have data storage and connectivity to a data source? Well, usually you have files flying around. You email files to people or you put them in a shared drive or whatever. And then somebody makes a change on the file and you don't have the latest and etc. It's a mess. It's a big mess. So this really helps to work in a serious way, in an enterprise way, to have this data storage and to have the connectivity that is handled by the platform. Then we have the idea of orchestration. So this is also maybe for a bigger project, but we can actually split different tasks, for instance, pre-processing, for instance, model training. We can split it in different scripts and have maybe different team members working on it. But also we can associate each task with different compute. Again, that comes back to the scalable on-demand compute. But that's interesting because if you need a GPU, if you need a memory optimized compute or CPU optimized compute for each task, you can decide to have something different. So that can be also quite powerful. Next, we have the model registration and management. And it goes hand in hand with the metrics registration because many times we use this, to make improvements on our models. And so we want to keep track a little bit like we do with, if you know, Git, GitLab, GitHub. You want to keep track of what's happening, the changes. So here again with the platform, we can register a model, we can keep a version of it and see what were the changes, what are the metrics that change. And imagine if you do, we do some hyperparameter tuning. So if you're not familiar with that, don't worry, we'll talk about it in the next segment. But sometimes you have just thousands and thousands of trials, different parameters. And so being able to register is very useful. Monitoring also is going to be part of the platform and part of actually Microsoft Azure. So we'll have another product, Application Insights, that we'll use to monitor our model. And we also have a monitoring part related to the data that we'll explore in a bit. And finally, model deployment. So that's made very easy in the platform. In a few clicks or in one click, you can deploy your model. So that's the platform Azure Machine Learning. The different parts of it, the different features. Now, again, another angle of seeing it is to see a bit the ecosystem. So data in, data out, or actually the products that come before and after, and also the audience of the platform. So I'll start with the audience because, as we said, there is this need of programming. So the regular data scientists, or sometimes we call them machine learning engineers, they should be able to program either in R or in Python. By the way, if you're wondering which language you should choose, I would suggest to choose Python. If you don't know either of them. So there is many of the things that are available in R as well on the platform, but it's just lagging behind a little bit. So if you're not sure, just go with Python. Safe bet. And so the data scientists are the primary audience of this platform. Okay, so they should be able to code. But we also talk about the citizen data scientist here. And citizen because they don't really need, they are not the primary audience, but they can still use the platform because of the no-code tools. So there are a couple of no-code tools that we are going to see, quite powerful actually. But those citizen data scientists, and even for any data scientist, but that could be a good way to do a quick prototype or a quick baseline. That kind of things that can be useful. So we don't want to exclude maybe business users or maybe statisticians who don't really know how to code. They're also welcome to use these parts of the platform. And finally, the platform is targeted also to the the DevOps, the software engineers. Those usually involved with orchestration, deployment, CI/CD, etc. Because they can integrate the platform with their current ecosystem. So that's going to be interesting. We're going to see that. Now, in terms of data, so what kind of data store we can use with the platform? So this is more like the data engineering part, but still interesting. So I would like to give you some explanations on that. So of course, it's a Microsoft product. So is going to be compatible with the the Azure product. And to start with the storage, so we have either a data lake or a SQL database as a source. That's the typical source. Why? Because if you have a data warehouse, then you use a SQL database. And if you have a lake house or a data lake, then you're going to use Azure Data Lake Store. So just comment that Azure storage is pretty much the same thing as a data lake store. Actually, a data lake is an Azure storage. It's just a parameter that is changing when you create it. But otherwise, it's pretty much the same thing. And here also we talk about Azure Cosmos DB. So this is not the typical storage that is used for Azure Machine Learning, but it can be used in a specific circumstance. Azure Cosmos DB is a NoSQL database, okay, that is used, for instance, if you have an app, a web app that you want to have a global reach, high availability and very reactive, very scalable, with replicas in many of the regions of the world. So you can use Azure Cosmos DB. But the thing is that the data will be stored as rows, okay, on the disk. Usually in analytics workload, we store the data as columns. So that's why in the data lake usually we use Parquet files. But Azure Cosmos DB has this option to create a hybrid transactional and analytical database. So that's one, that could be one way we use Azure Cosmos DB as a source for Azure Machine Learning. But usually we stick to the database, SQL database, or the lakehouse. Here we have some tools also thereafter, some tools that we can use to move data around. So they are all based on Apache Spark. Maybe you've heard of it. Apache Spark is a tool that is for data processing, but it's for parallel processing. Okay, so you write your code as usual, but under the hood, it's going to distribute your data and the compute on as many clusters as you have, as many nodes as you have, and it's going to be very powerful. So this works also to move data around. So Data Factory, you have a layer of no code on top of Apache Spark. HD Insight also, it's just Apache Spark, and Databricks, the original creator of Spark, is there. And by the way, Azure Databricks has also its own tools that Azure Machine Learning has. So just a parenthesis, if you're already in your organization, if you already have Databricks, have a look at what Databricks can do, because maybe you don't need an additional product, Azure Machine Learning. Maybe it's good enough for you to just use the machine learning capabilities of Databricks. I've seen customers, they do that. They just have Databricks. They do all their machine learning workflow there. That works very well. One thing though is that, for instance, Azure Machine Learning can be cheap and cheaper option maybe. So maybe you want to have both or whatever, but just think about it if you have Databricks. And then the output, so where your model is going to go, be deployed in a container. So either a container instance or Kubernetes service. We'll talk about those later. Or you can also deploy it in an application service. So Azure Function or Azure App Service is the typical one. So that gives you an idea of the ecosystem, what is before, after, what we can connect it, integrate it with, and also who is the audience, who is supposed to use this. And now I have a review question for you. What is Azure Machine Learning? It's the platform for operating machine learning workloads in the cloud, a service to spin up an R cluster in Azure, a tool to analyze algorithms developed on-prem, or an Azure service to access AI capabilities like computer vision. You all got the right answer. Azure Machine Learning is a platform for operating machine learning workloads in the cloud. The last one is actually a real product. It's called Azure Cognitive Services. It's basically a neural network as a service. You have an address, you can send your data to the neural network, and in exchange you get some results. But it's not a platform like we're talking about now, where we can build stuff. So good. You got the answer. So that was a little introduction on Azure Machine Learning, the machine learning itself. Now let's see how we can select our algorithms. So some of you are already familiar with machine learning, so that should be easy for you. Otherwise, we can simplify and say that there are broadly two categories of algorithms, the supervised and the unsupervised. Okay. So this is useful because there are many algorithms in machine learning. I mean, not thousands, but dozens at least. And so when once you have your business understanding, maybe one of the first questions you're going to have in your mind is, what kind of algorithm is there actually a way to solve this problem? And so that's why here we are going to explain a bit about that. And so the first kind is supervised learning. And supervised learning is the idea that we have some historical data. We have some historical data with the known output. Okay. So the example I gave you earlier on, imagine you have some historical data on the real estate market. So you have a number of houses, maybe the address, maybe number of rooms, surface, number of floors, etc. Year built. And then you have the price. So your known output, your known outcome here is the price. Okay. And based on all these parameters or features, you'll be able to deduce the price. So this is supervised learning. And this will be useful, for instance, if you want to build an app that, given a new house, gives you the market price, so then you can see if a house is undervalued or overvalued and decide if you want to buy it or not. But here, what makes it supervised is that we have historical data with actually what we want to predict. The known output is what we want to predict. And when what we want to predict is numerical, like that, continuous, then that's what we call a regression. So here I'm going a bit deeper in the classification. In the supervised learning, if what we want to predict is continuous numerical output, then it's a regression. If we want to what we want to predict is a discrete category, for instance, yes or no, then what that kind of algorithm is called the classification. Okay, so we have two kinds in the supervised learning. Regression, I want to predict something that is numerical, continuous. And classification, I want to predict something discrete, categorical. An example is anomaly detection. Imagine I have historical data on credit card transactions. And then at the end, I have a flag if it's a fraud, or yes or no. Yes, no, yes, no, yes, no. And so this is a classification problem where I can use my historical data with this known output to do a mapping between a fraudulent transaction with all the parameters, the variables of the transaction. Okay, so all of that is called supervised learning, when we actually have some label data. So maybe that's a lot to digest if it's really new to you, but just remember, supervised learning, we have some label historical data. We either predict something continuous or something discrete, categorical, and then it's either a regression or a classification. to give you another example of what we have on the slide here. So we have some personal data here, maybe the degree they have, their occupation, and we want to predict their income bracket. So this is supervised learning because we already have historical data, label data. Okay. Now, is it a regression or a classification? Here it's a classification because we don't actually want to predict their exact income. We want to predict a bracket, so a discrete category. You see here, less than 50K, more than 50K, etc. So those are categories. Okay, so supervised learning, classification. If we wanted to predict their, exact income, that would be a regression. But now we have also another broad kind of algorithms, unsupervised learning. And here we don't have any labels. We don't have historical data with labels. So imagine the transaction, the credit card transaction data set that we talked about. So somebody gives you like 1 billion or 10 million credit card transactions, and you don't know which one is an anomaly. And the goal is to find anomalies. So that would be an unsupervised problem. And there are techniques to do that. When we come back to the example I gave you at the very beginning, you remember the cargo ships between France and England, and we're trying to find which one were suspicious, fraudulent. Similar problem. We have a data set. We don't know which one is an anomaly. So there are ways, unsupervised learning. We can apply some techniques, unsupervised learning. But then we'll have to interpret the results. So that would be the difficult point. Another example of unsupervised learning is what you can see on the screen. You have a data set on the left, Maybe you have, here you have the number of square meters or square feet. And here you have the price. So X is square feet, Y is the price. And we're talking about houses again. And so you could create a clustering algorithm or use a clustering algorithm to create a model, unsupervised model, where your algorithm is going to create those different groups just based on the relationships in the variables of the data. So this is quite powerful actually because it's just using the actual data itself, its relationship between the variables, and then you have an output. So maybe we can sometimes, when I teach this, some students, they say, oh, but this is much more powerful than having to label each data and knowing if this is an anomaly or this is in the blue group or this is in the pink group. So yes, it's very powerful and supervised learning, but can be very difficult to interpret and to use if you don't have the business knowledge. Okay? Because here we've created 3 groups, but in the end, what do they mean? It's a bit difficult to know if you don't have the business knowledge. Another example in marketing. Marketing is very common to create groups of customers so that you can apply different marketing campaigns, different strategies, or different pricing. But if you don't really have the marketing expertise, you can just run your algorithm and you get 100 groups or 20 groups. What are you going to do with it? Okay. So really, if you go for unsupervised learning, you need to really understand what should be the output. To give you an example that I worked on that was successful, sometimes I had some success as well. I was working for a publishing company, so printing magazines, books, etc. And so the idea was to to predict the demand for each item, for each product, so that we could allocate some budget. And so one way of doing it is just to get all the data, and we're trying to predict demand, so continuous value, numerical value. So what kind of problem is it? It's a supervised problem with a regression. So we have historical data with our label already. We know how much we've printed in the past, etc. So we just apply a regression and we know in the future. But if you just get the whole data, you have, not the best results. Or you get a very, very complex model. So it's not the best. One thing that worked very well is, as a first step, to do some clustering, just like we see on the graph, on the slide, and to create groups. And here with talking with a business expert, we saw that the groups, they actually represented the patterns. So for instance, some items are periodical, so you have like a pattern that is periodical. Some of them are actually on the decline, some of them are rising, etc. So you actually have some patterns that you can relate to each group. And then it's much easier when you focus on one group to create a really good regression. So that was one way of applying clustering, and it was quite successful. But just to come back to the difference between supervised and unsupervised, if you're new to this, it's a little bit maybe difficult at the beginning. But again, supervised learning, we have historical label data. So we know in the past that those were blue and those were red. And we're going to use that knowledge to create a function that will link the value to the color. And this is the case when, for instance, you have credit card transactions and you have the flag for each transaction. In the past, you knew this one was a normal, this one was an anomaly, a fraud. Okay? So this is supervised learning. And again, you have classification for categories, regression for numerical values, continuous values. But if you don't have these labels on your historical data, if you don't have the category or the price, then you're going to have to use some unsupervised learning. And just looking at the relationship among the data, the algorithm is going to create groups based on the values that you have. And here you will need very strong business knowledge to understand what's happening. So, have you understood? Supervised learning uses what kind of data, where unsupervised does not? Numerical, labeled, categorical, ordered. Thank you. And it's clear for everybody. Good job. Now I want to finish this first segment with a small mention of the data-centric movement. So some people will say, oh, this is not really a thing. We've always been data-centric in machine learning, in data science. Well, other people would disagree with that. maybe if, like for me, I started machine learning 10 years ago. And at the time, it was the beginning of platforms like Kaggle, for instance, where, if you've heard of them, they do competitions, machine learning competitions, where they give you some data and you have to find the best model to predict or to fill the requirement. So the data is fixed, but then you need to iterate on the model and find the best model. And those really became very popular and really shaped also the culture in machine learning. And that's what created a model-centric way of thinking of machine learning. Get the data, okay, of course, you pre-process the data, of course, but then you try to improve your model. But these days, we get access very easily with libraries to very powerful models, and you can tune them automatically almost. Not almost, actually, you can. So there isn't much to win from, working on your model. So last year, the first data-centric competition started, where you have a fixed model, and your goal, your task is to change the data, to improve the data so that you get the best results with this fixed model. And that's what we call the data-centric movement. But we became we refocus on the data. We know that we can get really good models easily. Now we need to work on how we can improve the data, how we can collect the data in a way that it's better quality data, how we can feature engineer the data to get a better model, how we need to monitor the data to know when we need to retrain or when we need to find new features, etc. So now it's more about the data. Of course, the model is important still, but there's a slight change in the paradigm. So having said that, let's look at the machine learning platform together. So I'm going to share my screen, and